Welcome all. TCS seminar at the Jagiellonian University. Today, our first speaker today is Amadeus Reinald from Montpellier. He's about to finish his PhD on the supervision of Stéphane, Bessy and Daniel Gonçalves. And I imagine that you will talk about some of this work, which will get the... Happy to have you here. The floor is yours.
Thank you. And thank you, Piotr and Bartosz, for having me here. I'm glad to come to Krakow. And today I'm going to talk about conjecture by Burr about oriented trees in digraphs with large chromatic number. So this is joint work with Stéphane and Daniel, for my PhD supervisors in Montpellier. So the general question which a lot of people ask, even here in this lab, is what structures are forced by high chromatic number? So if you ask this for minors, there's a conjecture by Hadwiger that chromatic number k should guarantee you that you have a clique minor in graphs. For subgraphs, it's easy to see that if you have chromatic number k, the only thing you can guarantee are trees on k vertices, which I will call k trees in this seminar. For induced subgraphs, it's a more asymptotic conjecture by Sumner that if you have large enough chromatic number, infinite, you will get either a large peak or any tree as an induced subgraph.
So I forgot to do the slide sharing on Zoom. Let me just quickly do that. Terrible. Are we on Zoom here? Probably not.
I'm trying to do it on your board.
No. It's everything is set up. It just didn't come. Yes.
Do you want me to start over?
No. Please. Apologies. Okay.
So as I was saying, so you have three ways to ask this question for graphs. You have more ways, but let's say the three main ways are asking for minors, subgraphs, or induced subgraphs. And so these are two big conjectures. And the middle one is actually pretty trivial. I will show it on the board at some point. But in this talk, we're interested about directed graphs. We want to find directed subgraphs for chromatic number larger. So do you have a constant such that if your chromatic number is bigger than the constant, you find all directed subgraphs, all oriented trees as subgraphs. So this is generalizing this question, but it becomes non-trivial in directed graphs. Okay, so the first question is if you have a graph H, do you even have a constant such that a large chromatic number gets you this H as a subgraph? And there is this construction which probably many of you are familiar with of Addario-Berry and Reinald of graphs that have arbitrarily large curves and chromatic number. So if your graph H that you want to find in high chromatic number graphs is contains a cycle, then you just take graphs with curve larger than the size of the graph and the large chromatic number, and they will not contain H. So this question cannot be asked for anything that contains a cycle. So this is why we are only interested in trees. And now this is for undirected graphs, and for undirected graphs, it's pretty easy to see. I will draw it on the board how to find all trees. So say I have G with chromatic number K. And I want to find all my trees of size K. So I take my color classes. 1, 2, 3. Okay. And what I do is that I start with the first color class, and I will try to put as many people as possible onto my first color class. So if a guy here in color class 2 does not have neighbors here, I put it here. So this is like stacking the first class onto the second one. Then if I have a guy here that has no neighbor in 1 or 2, I put them, so I take vertices one by one from increasing classes and I put them to the lowest class to which they can belong. So this is like, I stack my coloring. So if I do this, and then I look at class I, and have fully stacked my neighbors, then it means I have neighbors to everyone here, right? Otherwise I could have moved it. So I have one neighbor. Yeah, there exists one neighbor. So then if I want to build my tree, then it's pretty simple. I just say I root it here. Or like, okay, say I have my tree T, and I can build it as some leaf plus some T prime, which has size 1, T minus 1. And so here by induction, until class K minus 1, I can find T prime. Okay, it's pretty easy to see that if T prime has size 1, I can find it in class 1. And now I know that T is built by adding just one leaf to T prime. So, wait, what am I doing? So actually I find T prime. I find T prime here on the last K classes. These are also stacked, like this is. And then I look at wherever my leaf can appear. So like say I managed to build my tree like this. This is not interesting. Okay, this is my T prime. And then I want to add a leaf anywhere. Well, of course, every guy here has a neighbor in class 1. So I can say I want to add this leaf. I just add it. This is the leaf that I just added. Yeah. So, and of course, if I do not, this is because I have chromatic number K. If this stacking here, if I have K classes because I had chromatic number K in the beginning, I cannot hope to, when I do this stacking of colors, I cannot end up with less than K classes like this, even after the stacking. It's still a proper coloring. So this, this gets me all trees of size K. So this is for graphs, and it's pretty easy. It's one of the proofs, but perhaps the most I don't know, intuitive one. But there are other ways to prove it. You can extract a graph with high minimal degree. So what happens now if we ask the question for oriented trees? So we consider digraphs, but we don't consider dichromatic number. We consider the chromatic number of the underlying graph. And we ask if still, if we can find structure from the usual chromatic number. So we know that for high chromatic number, the only graphs we can hope for are trees, because of these high girth, high chromatic number examples. Now, for digraphs, if we ask the same question, still for undirected chromatic number, we cannot hope to find more than orientations of trees, right? Because if you remove the directions, you also find them as a usual graph. Okay. So the question becomes, for any k, do you have some f of k such that chromatic number greater than this gets you all oriented trees on k vertices? And if you try to do the same technique as before, I will not go to the board, but if you try to do this, let's call it color stacking technique, where you start with a coloring. Okay, maybe you have plenty of colors, but you stack color classes as long as there are enough edges and you get some kind of enough choice between these edges to build anything. Well, now, of course, you have no control on the direction of your edges, so you cannot you cannot hope to. The way we built our tree there was really from right to left, and this is the only way we could build our tree. Now, you don't have guarantees. Like maybe the directions now will force you to go either left or right, and you can't do this anymore. But still, Burr showed that if you have chromatic number quadratic in K, then you contain any K tree, oriented K tree. But he conjectured actually 2K minus 2 should be enough. So this is like just twice the chromatic number that we require for undirected trees. So you just double the chromatic number, and you should get every orientation of the tree on K vertices. So this is like, yeah, for any digraph, for any oriented graph, such that the underlying graph has chromatic number 2K minus 2, you should find any oriented K tree. So this is tight because, like here, you find an example of chromatic number 5 without a tree on 4 vertices. And there is so Burr showed this quadratic bound, and there's been a factor 2 improvement by Luigi Addario-Berry, Frédéric Havet, Claudia Gonçalves, Bruce Reed, and Stéphane Thomasé, which really uses nice techniques, and we will see some of the techniques now. So there are multiple ways to, let's say, attack this conjecture. One is to restrict the host of directed graphs you ask the question on. So if you only ask the question for DAGs, directed acyclic graphs, then actually you find all K trees. And I will sketch you this afterwards. If you consider the class of tournaments, this is actually asking for chromatic number 2K minus 2 becomes asking for size 2K minus 2. And this is the conjecture by Sumner from a bit before Burr's conjecture that says that yeah, exactly 2K minus 2 should get you all K trees on oriented K trees. And it was solved for large enough K by Kuhn, Mikroff, and Ostius, and it was shown like by a Porter proof, and actually for all cases that 3K minus 3 works by SAD. So yeah. The other way you can attack the conjecture is you restrict the trees you are looking for, and you see. So now you consider the class of all directed graphs. You ask if they have large chromatic number, can I find like what are the trees that I can find? Maybe I can't find all trees on K vertices, but maybe some of them are okay. So there is this, let's say, famous. That's because I'm doing digraphs. Theorem by Galay-Roy, Haas, and Vitaver, that the chromatic number D, K, in D, gets you a directed path of length K. So this is really insightful, and like initially surprising when you, like it is the first example of a chromatic number of the underlying graph gets you some directed structure to be forced, which is initially is quite surprising. But, yeah. Chromatic number K also gives you paths with 2 blocks, which are paths that can be split into 2 directed paths. And for 10K, or something like that, maybe 8K, you get paths on 4 blocks. So these are paths which can be split in 4 blocks for directed paths of length K, and anti-directed trees. So anti-directed trees are those oriented trees for which either vertex is either a source or a sink. So yeah, and yeah, the techniques really have nothing to do with one with another. And, yeah. So what we show is so an improvement on the quadratic bounds, that if you have some chromatic number greater than K square root of K times the constant, then you can find, in general, you can find any oriented K tree. So then we have better bounds for paths with B blocks and arborescences. we will see first the case of arborescences, but I will discuss a bit about existing bounds. Do you have any questions? Like, don't hesitate to interrupt me if I'm not clear or if I lie.
So, if you think about paths that are oriented in an alternate fashion, do you have any bound?
So these will fall into anti-directed trees.
Anti-directed trees. Yeah. Oh.
But if now you consider a path that is like alternating like b times, then it's path with b blocks.
Yes, yes.
But we don't have a bound that does not depend on the number of alternation.
Also, the blocks. So you don't have a general result for anti-directed trees. It's
no, for anti-directed trees, like where like every vertex it alternates at each vertex. This we know there is a linear bound.
There is a linear bound. Okay.
But now, if you even like subdivide once these guys, then it becomes okay. Now subquadratic, but you don't have a linear bound. Actually, no, I don't think you have a linear bound. Yeah. So yeah, we have these improved bounds so for paths with B blocks and arborescences, but in general, like the main thing is that there's a subquadratic bound for oriented trees. So let's talk a bit about existing bounds. So like, what are the first graphs we may be able to find if you have large chromatic number in a digraph? Well, the first observation is that if you have a chromatic number greater than 2k minus 2, you have an out star of size k necessarily. Why is that? Because otherwise it means every vertex in your graph has degree plus at most k minus 2. Actually, if you sum the degrees, this bounds your number of edges. And so you have maximum average degree twice that. And this bounds your chromatic number by 2k minus 2. And in another direction, so there is this Addario-Berry theorem, which I mentioned, that for chromatic number k, you get the directed path of length k. And this is, I can sketch the proof, but maybe I will sketch another thing. I can sketch it later if you want. But it's like you start from a BFS, and then you like manage to unstack every layer of the BFS into some independent set, and then it gives you a coloring. So if you have k colors, you are forced to find this directed path.
In terms of BFS, is there a digraph notion of BFS, or is this just like a graph?
No, it's a directed BFS. So okay. I mean, I can sketch it. I've already sketched it to Google. So you start from this any vertex here, and you look at all its out neighbors. Then from these out neighbors, you look at all the out neighbors, and so on. So this is like the usual BFS. This is actually a BFS. Then what you do is when you have an edge here, so you want to turn each of these layers into an independent set, ideally. And so if you have an edge here, what you do is you say, okay, let me look at where it arrives from. Let me look at where it goes, like what's the subtree here that's coming out of it. And let me just kill it. I mean, I kill this, and I switch it, and I put it onto the next layer. Okay. So like I move, if I can reach some vertex in one step more, I push it further down. And then this ensures that I have removed all my arcs in every layer. So it's not a BFS anymore. But now every class is an independent set here.
So if this BFS is in the directed graph, as you say.
Yes.
So there might be some edges from later layers to layers before.
Yes. Maybe you have edges from here to here.
easier to just say that f of k is the length of longest path terminating at k, and that this is or f of v is the longest path, length of the longest path terminating at v.
And this
is
also
a proper coloring of the underlying.
Yeah. I mean, I don't know. Like you still have to check that it's actually a proper coloring, but I know there is this proof too.
You have to kill samples, yeah.
I don't care about samples.
So what is the largest path?
I mean, the largest path is the largest value of this function text. The length of the longest path.
Ah, so you're not allowed to reset the processes, okay? Yeah.
I don't understand the issue.
Yeah,
No, this works also. I don't know, I prefer this proof. Like I like this decomposition, but yeah, it's maybe it's cleaner also. But yeah, so like the two reasons for which we got these like the path and the star are very different. Like we had some maximal some density argument that made the maximal average degree is high in one case, and in the other case it was some in this case some decomposition. But yeah, there are really orthogonal, the two orthogonal kind of oriented trees, and the techniques are very different in terms. So yeah, let's first I will give a rough sketch of how you find oriented trees in DAGs. So this is like one of the first restrictions as I mentioned. And so if you have a directed acyclic graph, so my goal is I have a DAG with chromatic number k, and I want to find any oriented tree on k vertices. And so what can I do here? So I take my DAG, and let's say by induction, let's say chi of DAG greater than k minus 1 gets me t prime outside k plus 1. Good. Now I take this DAG here. The DAG and chromatic number greater than k. And what I will do is, okay, I consider any tree. My goal is to find some tree T, which again is built by adding, say, without loss of generality, one out neighbor to a tree T prime, which has size k minus 1. So I would like to, I know I can find T prime here, but I want to find T prime in such a way that I can go out from T prime. And actually, I will manage to find a way that I can go out of every vertex of T prime. So what do? So this is an out neighbor, right? So here in my DAG, I have sinks, and sinks, like there is no way I would my T prime we need to glue. I can't glue upwards, right? So I take these things and I kill them. Right? I take them, I put them aside. And so these, if I manage to find my tree in this neighborhood, then I can glue it. But of course, they don't dominate my whole set. Like I can't. They are just sinks. So maybe I have guys here, which have a path towards a sink, but they are not. If I find my tree T prime here, I can't glue directly a sink. But what I do is, okay, at the next step, I have these guys that are indominated. So this is like, these are good, okay, I don't care. if people are here, I can glue to them. So I remove this. So I remove the next layer, so which are things at the next step actually. And now, so like these are the first things, right? Thing 1. And then like the guys I indominate are actually just the things at the next step, right? If I have a sink after I removed S1, it means that so I wasn't a sink before, so I have an out vertex towards those. Okay, so maybe I indominate more, but at least I indominate those. So I take these next things and I keep them in the graph. Okay, but so okay, they are okay. So these are S2. I keep them. And then at the next step, I will take the following things. So again, I take those apart, the things at the second step. But at the third step, I consider, so this, I have things here, but I keep them. But now I consider the things at the third step. So this is kind of layering my diagram. And those will, again, indominate a part of what's left. But more importantly, they will not be, okay, so if they were indominated by my first things, then I don't. So okay, no. When I remove these things, I consider as okay any vertex that is indominated by my things. Sorry. So I only consider. So I consider G minus n minus of S1, and in this, so G, sorry. And in this graph, so these are the guys that are not indominated by S1, and in this graph, I will consider things again. So sorry, so it's not very clear for the drawing, and I don't know how to do the layering at best, but I take my first things, the indomination set, I remove the set that is indominated, then I take things in what's left. So let's call them actually S2. And then I remove those. But those are things after I removed S1 and indominated by S1. So they cannot have edges to S1 because they would have been indominated. So this gives me a second set S2, which itself dominates some n minus of S2. And I remove them, like this is okay, I can glue to this, and so on. So I take S3. I take S3, which indominates again some part, but again, so it wasn't in the neighborhood of those, so I can remove them. And at each step, this here, S1, S2, S whatever, is actually an independent set. So if I remove it, I can't drop the chromatic number of my graph by more than 1. But it's an indominating set. So it means every graph that every vertex that is left in my graph after I removed all these SIs, I can go out of it towards one of the SIs. But I only paid chromatic number 1 for this. So this gives me my count. I remove it, I have chromatic number k minus 1, and now I pay one independent set to be able to glue my leaf. Is it okay? So So yeah, like this is one restriction. So DAGs are nice, and actually this was remarked in the paper by Addario-Berry et al. And they used it like quite a lot in their proofs, and we will use it as well. So the way Burr and the Addario-Berry et al. Paper works is, so for the general bound in general digraphs, this quadratic bound. Why, if you have chromatic number quadratic in K, you can find K tree. And it works by induction with the following operation, which, if you have a bound for a given tree, it's an operation that gives you a bound for the tree built by gluing leaves to it. So what do I mean by this? So assume you have some tree T here in purple, and you know that chromatic number C gets you T. Now, what they showed is chromatic number C to the bound of P4 plus 2 times K, 2 times Q plus L, but this is actually 2 times the size of the final tree, gets you the initial tree glued with L out leaves. So 2 times Q plus L, so 2 times the size of the tree before plus the number of leaves I want. If I pay this on top of my chromatic number, I can get this much more structure. So this many leaves more I can get for this loss.
So these leaves are, do we have control how they are?
You can put them anywhere you want. Yes. You just need L leaves, but you place them anywhere you want on the tree. So this is really powerful. Like, you can build, like, if you have an arborescence that is branching a lot, then you can really glue a lot at each time.
So does this imply if you're looking at trees of bounded height, you can get linear bounds?
Yeah.
Yeah.
Yeah. Even like bounded height. Yeah, because of course this operation, like here I say I glue out leaves, but you can glue symmetrically. You can glue in leaves. So if your tree, you can decompose it by removing out leaves, then removing in leaves, and a few number of times, then you have a bound by the height. So how does this work? Well, we already saw like one kind of similar example, which was the star. Like the star, the way we managed to find the star from high chromatic number was by some density arguments. So here we will do the same, but now we want some rooted star, right? We want to find the tree T, and we want to glue like stars all around it, kind of. What you do is you take your digraph with the high chromatic number, so the highest, and you split it into 2 parts. Those guys that have low out degree, Q plus L at most, and those that have a high out degree. And by the same arguments as before, like this guy has a small average degree, so it has more chromatic number. Actually, it has less than 2 Q plus L minus 1, but okay. It has just enough so that in the rest of the graph, it has chromatic number at least C. And so this means, this means you can find your tree T here. But now your tree lives in a world where everyone has high degree. But it's actually like super high degree. So that, let's say you want to glue this top 2 out leaves there to this guy. Then, okay, you have, maybe you have high degree, but you go towards yourself, right? The snake that bites itself. But you have larger out degree than the size of the tree that you are looking for. So you will always find things that are available. And you go to the next one, maybe it conflicts again, but you ask for just enough out degree that you can continue and find more available alternatives. So that's the lemma. And is it clear? So I have a bound for a given tree. I pay a constant. Okay, I pay 2 times k roughly, times the size of the final tree, and I get a bound for my new tree. So this can be used to derive the quadratic bound immediately, because yeah, I mean, as Robert was saying, it's bounded by the depth. So at each step, the operation costs k, at most the size of the final tree, or like 2k or something. And so you can just remove an out leaf or in leaf at each step, and you will pay k to glue it. And you do this k times, and this gives you, this gives you this k squared bound. So this is the calculation. So this is good. We already talked about this. This is good when t is close to a star or when a tree has low depth. This gives you a good bound. But it's really bad for directed paths. Like if I had just the directed path from Galilei, the one which I know how to get with chromatic number k, then at each step I can only remove one out leaf or one in leaf. I can never remove two out leaves or two in leaves. So I have to do really k steps and to pay this quadratic number in full. So yeah, so we have these two orthogonal kind of directions, like these paths which are easy to get, this, like out stars or high degree vertices which are easy to go. But how can you combine the two? And so I will show you how we did this for arborescences, but the general case is just a bit more technical, but it's a pretty simple idea. So,
sorry, what's the definition of the arborescence?
Sorry, so an arborescence is
so
exactly
a tree that all goes one direction?
Yeah, I mean, so you have one source vertex, and then like towards the leaf you have a directed path. So the only things are the leaves. And yeah. So I will show our subquadratic bound for arborescences. Yeah. So assume by induction you have some. So this is not the most rigorous kind of proof, but I don't want to put the actual numbers on the screen. But I assume you have managed to prove a k square root of k bound, q square root of q here with a fixed constant, not a big O.
Sorry, is q also corresponding to the number of vertices in the arborescence?
Yeah. So assume for arborescences of size q, you manage to find q square root of q bound. So it's not a big O, it's like a fixed constant. Okay, I assume you have your bound until size q. Now you take a tree of size k, larger than q, and so there's only one thing you can do at this point is you remove the out leaves from t. It's an arborescence, so you can remove all leaves by removing out leaves. So you get t prime here, and you recall the bound of before, and so this means that so you have a when you remove the out leaves here, you get your tree t, the purple one, which you know how to do in q square root of q, because it's more than k. And now you know that you managed to add all the leaves for 2k. Right? So you have a small tree here that you know how to do in subquadratic, and you know that you can add a lot of leaves, and this costs you 2k. But actually, this time, sometimes this is good, right? If you have more than square root of k leaves, then the amortized cost of this operation is you pay square root of k per vertex, right? So this preserves your bound. Like, you don't have to do the calculation. You do one operation, you add square root of k vertices, and you pay just 2k. This is still a k square root of k bound. So now, what happens if we don't have many out leaves? So we know if we have a lot of out leaves, okay. But if your tree doesn't have more than square root of k out leaves, what can you do? In fact, it's pretty easy to see that if you have L out leaves, so let's say these are all the leaves of your tree, then actually you can split the edges of your tree into L directed paths. Because this is an arborescence, right? So I start from here. Okay, so what do? I just start from the root, I go to the first leaf. No, actually, I start from the first leaf, I go to the root. Then I start from the second leaf, I go to the first thing available. I go to the third leaf, I go to the third thing available, and I just prune my tree like that. L operation. Good. So if I have a few number of leaves, I can split into a few directed paths. But this tells us nothing because we saw that the directed path costs a lot. Like if you want to glue the directed path with their operation of leaf gluing, you have to pay at each step. So this is quadratic, this is bad. So you need a new ingredient, which is how to glue a path. Instead of gluing leaves, you glue path. And this is like really the orthogonal operation. And what we show is that with kind of like the same bound as before. So assume you have Q vertex trees for chromatic number C. Then you can get the same tree with a path of length S glued to it by paying 2K, roughly. So 2 times the size of, you add 2 times the size of the final tree, and this gets you this allows you to add a directed path. So how does this work? Here we will use the DAGs that we showed had you could get anything of size k if they had chromatic number k. So you take a maximal DAG in your graph. Now, if this maximal DAG at any point, had chromatic number greater than k, then we are done. So we know this DAG has chromatic number less than k. And what we know also is that because it's a maximal DAG, any vertex outside has both an out neighbor and an in neighbor. This is actually useful because, like you see it coming, we will find the tree. We try to find the tree in this zone, and if you have a lot of out neighbors to this green zone, then it's useful to glue a path to it. But how do you find this path in the DAG? So we saw here like a technique where you take an in-dominating set and you can build anything in your tree. But this is not actually what we'll do. We'll do something much simpler. Is you layer your DAG like from so that all the edges go, all the arcs go from left to right, and you take the sinks. Just the sinks. I stop here. These sinks, okay, maybe they in-dominate some people, but anyhow, any guy here has a path that ends up in a sink, by definition. So any guy here, when I remove the sinks, any guy here starts a path of length 1. Right? This is not too much for now. Now the problem is that, okay, maybe you had a vertex here outside. So again, the goal is to get the tree here by induction and to get it here, because we'll have large chromatic numbers. Now the problem is vertices outside to which you want to glue the path. Maybe their neighbors get eaten up. This is not an issue for now, but maybe because you remove this, your vertices outside will end up having neighbors here, and you cannot glue paths to them. The only thing that you are guaranteed is that in this green zone, everyone starts a long path. Okay, for now it doesn't start a long path. So what you do is you include back those vertices outside. So actually what this means is you remaximize the DAG. Like if you have a maximal DAG, you have the property that every vertex outside has both an out neighbor and in neighbor. Now you kill the part of your DAG, so it's not a maximal DAG anymore, but it's still a DAG, but you just remaximize it greedily, as you wish, and you get this property back. That's it. You can glue in both directions from any vertex outside. And you just keep going. Like you remove the sinks at this step. Okay, so I'm hitting some technical detail on the rug, but it's not too complicated. But at each step, actually, you remove a set of sinks, which will cost you, it's a set of sinks, so there are no edges between them, so it costs you chromatic number 1. And these guys will have increasingly long paths that start from them, because they will have a path towards this guy, and then this guy will have a path towards this guy, at least one path towards this guy. And you keep going, you remaximize, you remove the sinks, you remaximize. And at some point, you do this S times. So let's say you want to do a path of length S. You do it S times. So you pay chromatic number S for this. You pay chromatic number K, the tree you are trying to find for this DAG, because otherwise you are done. You have a DAG with high chromatic number. And so, by the way we chose our bound, you have chromatic number at least C in what's left. So you find a tree that has both an out neighbor and an in neighbor, but like it has an out neighbor to this maximal tag. And now this guy has a path to the sink, and you just continue the path however you like, but maybe you're done even before reaching the last step. And this allows you to glue your long path. Is it okay?
So why was it important to have an edge from the DAG to the rest up?
So this is not important like at any given step, but like once I start removing okay, so like the bad answer is that, like you can get this for free, that you have edges in both directions. The more like on-topic answer is that this will be useful in the general case, like for the proof. This is for arborescences. So it's just a restriction of the general case. But actually, so there is a step where I didn't go into too much detail here. So there, when you add a vertex back into this DAG,
yes,
you want it also to start a directed path of length 1. Because you want to maintain on this DAG the property that they all start a long directed path. So if you didn't have this wait, yes. No, okay. Maybe it's not exactly on topic, but if one vertex had only out neighbors, you could add it to the DAG and still be a DAG, right?
Yes, I understand that from the maximality you get it, yeah.
But why do you need it?
Probably you're using it somewhere because this would be very suspicious, yeah. But it's I also don't, yeah.
I mean,
we can discuss this detail.
Yeah, we can discuss it later if you want.
It's okay.
I know it's useful in the general case. Maybe we could get rid of it. So yeah. Sorry. So this is like okay. So this I managed to glue a long path. Okay. However long path, a path of length S by paying less than 2k, which is the size of the final tree. So this is like kind of same situation as for leaves. So if I have less than square root of k paths, then I'm happy. I split my graph into less than square root of k. I pay 2k per path, and I get my k square root of k bound. Okay. I mean, this is the summary. So by induction, my induction is just I take any tree. If I had more than its square root of its size in leaves, I glue leaves, and this maintains my bound. If it has less, then I can split it into few direct paths and I glue them, and this gets you actually even better than 2k square root of k. And paths with B blocks, well, there are paths which partition into B directed paths, so you can just do B operations. And if you tweak it a bit, you get B over 2. So yeah, I think my time is done. If you want to discuss the general case, we can discuss it later, but it's the same idea. It's just the gluing is a bit more technical. But yeah, and so for open directions, like even for directed oriented paths, we have no better bound than k square root of k right now for general oriented paths. this is still annoying. And in general, like the hard thing for us is trees that require a lot of leaves gluing and a lot of paths gluing. And these are like, take a star which is subdivided square root of k times and has degree square root of k. Then this, whatever operation you do, you will not do much better than k square root of k. So yeah, dziękuję. Thank you.